The universe is supposed to build itself slowly. Small clumps of matter gather first. They merge into galaxies. Galaxies merge into clusters, brick by patient brick, over billions of years. That is the rulebook, the standard model of cosmic growth, trusted for decades. Nothing big should appear early. Then James Webb pointed its mirror at the dawn of time and found a cluster of galaxies already bound together, already behaving like a mature neighborhood when the universe was less than 5% of its current age. Scientists called it a preview of a fully grown galaxy cluster. According to every timeline they calculated, it should not exist yet. And here is the part that really gets them. It is not alone. A wall of galaxies 10 billion light-years across, an arc reaching nearly a third of the way across the observable universe, a ring sitting almost exactly on top of that same arc. Every one of these structures breaks the same ceiling. The size limit the standard model says nothing should ever cross. That model is not a footnote. It is the backbone of how we measure the age of the universe, the amount of matter in it, the shape of reality itself. If the backbone has a crack, everything built on top of it wobbles. So we are going to look at the actual evidence, the numbers, the calculations, the theories fighting to explain the gap. And then we are going to ask the question nobody has answered yet. How did the universe grow up so fast? Deep inside one of the sharpest pictures ever taken of the sky, there is a knot of galaxies that should not exist. Not yet, not this early. The image came from James Webb, the most powerful eye ever pointed into deep space. The light in that frame left its source before our planet even existed, and what it shows breaks every rule cosmologists have trusted for decades. These galaxies are not just sitting near each other, they are bound together, already behaving like a mature neighborhood when the universe was barely old enough to have a first birthday. Scientists called it a preview of a fully grown galaxy cluster. A preview that, according to every timeline they calculated, should not exist. Yet, there it is. Caught on camera, confirmed, and refusing to make sense. Here is the problem in plain terms. The leading model of how the universe grew says, structure builds up slowly, step by patient step. Small clumps of matter gather first. Those clumps merge into bigger groups. Groups merge into galaxies, and galaxies slowly merge into full clusters over great stretches of time. That process is supposed to take billions of years before anything resembling an organized, massive structure can exist. But this cluster showed up already looking mostly finished, at a moment in cosmic history when it should have barely begun. This is not one strange picture sitting alone in a folder somewhere. Similar, oversized, oddly organized structures keep turning up survey after survey, both from ground telescopes scanning enormous patches of sky and from Webb staring into tiny, deep patches with incredible sharpness. Each new case adds pressure to the same question. If the universe only had a limited amount of time to build things, how did anything get this big, this early, this fast? Hold on to that question, because it only gets heavier from here. Here is the number that stopped astronomers cold. The galaxies bundled into this cluster already carried a combined mass equal to hundreds of billions of times heavier than our own star, all locked together while the universe was still less than 5% of its current age. Picture a toddler already running a marathon. That is roughly the scale of the mismatch between what was expected and what showed up on the screen. Researchers studying the image openly described it as a preview of a fully grown galaxy cluster, the kind of dense, sprawling neighborhood of galaxies that normally takes many billions of years to assemble. Finding a working preview this complete, this early, felt less like spotting a toddler taking its first steps and more like spotting a grown adult standing exactly where a newborn was supposed to be. This matters because the model being questioned is not some obscure footnote in a textbook. It is the backbone of nearly everything modern astronomy assumes about the age, size, and shape of reality. If that backbone has a crack running through it, the crack does not stay small or contained. It spreads into how we calculate distances across the cosmos, how we understand the invisible matter holding galaxies together, and even how we picture the opening moments of existence itself. That is the size of the stakes riding on one oddly grown-up cluster of galaxies caught on camera. Before we can fully appreciate how strange this discovery really is, we need to clear up something most people misunderstand about staring into deep space. Pointing a telescope at something impossibly far away is not simply looking at a distant place. It is looking directly into the past, frozen and delivered straight to your eyes, and that single fact changes everything about how this story should be read. Every photograph of deep space is really an old photograph, and almost nobody thinks about it that way. Light does not travel instantly, it moves fast, but it still takes time to cross the gap between one place and another. That simple fact turns every telescope pointed at the sky into a kind of time machine, one that shows you the universe exactly as it looked the moment that light left its source, not as it looks today. Think about how this plays out close to home first. When you glance at the night sky, you are seeing starlight that is already years old by the time it reaches your eyes. Now stretch that idea across billions of light years instead of a handful. The farther away something sits, the older the light arriving from it becomes, and the further back in cosmic history you are actually peering. Distance and time, in astronomy, are the same measurement wearing two different names. This is exactly why the discovery in the last chapter felt like such a shock. When astronomers measured how far away that mature-looking cluster sat, they were not just marking a location on a cosmic map, they were reading a timestamp. The light reaching the telescope's mirror left those galaxies roughly 650 million years after the beginning of everything, a sliver of time compared to the universe's full age today. Seeing developed structure at that timestamp is like receiving a photograph and being told it was taken decades before the camera itself was invented. Astronomers pin down these timestamps using something called redshift, though you do not need the technical term to understand the idea. As the universe expands, it stretches the light traveling through it, shifting that light toward longer, redder wavelengths. The more the light has stretched, the longer it has been traveling, and the further back in time its source sits. It works almost like a cosmic odometer built into every beam of light that reaches us. Catching light this old is the entire reason the James Webb Space Telescope exists. It was built to detect the faint, heavily stretched light coming from the earliest galaxies, light too dim and too shifted toward the red end of the spectrum for older telescopes to ever pick up. Every time this observatory breaks a record for the most distant galaxy ever found, it is really breaking a record for the deepest look backward in time that human instruments have ever managed to achieve. Once you accept that every deep space image is a message from the past, the real question becomes obvious. How far back can astronomers actually see? And what should the universe have looked like at each of those checkpoints along the way? That question is what makes the next part of this story so important, because scientists did not just guess at an answer. They built an entire model, backed by mountains of observation, that predicts exactly how the universe should have grown at every single stage. And that model is about to run headfirst into everything we just described. Cosmologists did not invent their model of the universe from a hunch. They built it from decades of observation, and today it stands as the closest thing science has to an official rulebook for how everything from atoms to galaxies came to exist. That rulebook is often called the Standard Model of Cosmology, and its central idea is almost stubbornly simple. Structure in the universe grows slowly, from small to large, never the other way around. Here is how the process is supposed to unfold. Right after the beginning, the universe was almost perfectly smooth, with only tiny differences in density scattered here and there, like faint wrinkles in an otherwise flat sheet. Gravity then got to work on those wrinkles. Regions with slightly more matter pulled in slightly more material from their surroundings. Over enormous stretches of time, those regions grew into clumps, the clumps grew into filaments, and the filaments eventually wove themselves into the sprawling cosmic web of galaxies we observe today. A huge, unseen ingredient drives most of this growth. Scientists call it dark matter, invisible material that exerts a strong gravitational pull despite giving off no light of its own. Under the Standard Model, dark matter formed the scaffolding first, and ordinary matter, the stuff that makes up planets, stars, and people, fell into that invisible scaffolding afterward, like water filling the cracks of a riverbed. Without that dark scaffolding, most models agree galaxies never would have formed fast enough to look the way they do now. This model is not some fringe idea waiting to be tested for the first time. It has passed an enormous number of checks, matching the patterns of ancient light left over from the early universe, matching how galaxies cluster together today, and matching the observed rate at which the universe is expanding. Confirmed observations back up huge portions of this framework, which is exactly why any crack in it deserves serious attention rather than a shrug. Some of the strongest support comes from a faint afterglow of radiation released roughly 380,000 years after the beginning, an early snapshot of the universe long before any galaxy existed. Every wrinkle and ripple in that ancient glow lines up with what the Standard Model predicted, in many cases before anyone had the tools to check it directly. That kind of successful, advanced prediction is rare in science, and it is a major reason this model earned the trusted status it holds today. But here is the part that turns this rulebook into a countdown clock. Because structure is only supposed to grow gradually, the model makes a testable prediction. It tells scientists roughly how big any structure could possibly get given how much time has passed since the beginning. Go bigger than that prediction allows, in less time than the model permits, and something is wrong somewhere. Either the observation is flawed, or the rulebook itself needs revising. That single testable prediction is the thread this entire investigation hangs on. Before we can measure whether Webb's discovery breaks the rulebook, we need to understand one more piece of the puzzle first. We need to know why cosmologists believe the universe should look smooth and even once you zoom out far enough, because that belief is what sets the actual size limit we are about to measure everything against. Zoom out far enough, and the universe is supposed to become almost boring. That single idea sits underneath nearly every equation modern cosmology relies on, and most people watching a documentary about deep space have never once heard it explained. Astronomers call it the cosmological principle, and it makes a bold claim. No matter which direction you look, and no matter how far out you go, the universe should appear roughly the same everywhere, smooth, even, and free of any single structure so large it dominates the view. Think about sand on a beach. Pick up a single handful, and it looks lumpy, uneven, full of individual grains clustered in odd little clumps. Step back far enough, though, and that same beach becomes a smooth, uniform stretch of tan reaching toward the water. Cosmologists expect the universe to behave the same way. Zoom into a small region and you find messy clusters, filaments, and empty voids. Zoom out to a big enough scale, and all that unevenness should blend into a smooth, uniform average, with no clump so dominant it throws off the whole picture. This is not just a tidy assumption cosmologists made up for convenience. It is baked into the math used to measure the universe's age, its rate of expansion, and the total amount of matter and energy filling it. Nearly every calculation depends on treating the universe as roughly uniform once you zoom out past a certain size. Break that assumption, and you are not just adjusting one small detail, you are pulling on a thread that runs through almost the entire field. That is exactly why the size of any single structure matters so much. If a clump, wall, or ring of galaxies grows large enough compared to the observable universe as a whole, it stops behaving like ordinary local unevenness. It starts behaving like a structure that could bias entire calculations, because a big enough clump distorts the average instead of blending into it. Confirmed observations from countless galaxy surveys show the universe really does smooth out eventually, but only past a certain scale, and that scale has a rough number attached to it. Astronomers did not leave this rough number as a vague feeling. They calculated it, using the age of the universe, the known speed of light, and the pace at which everything is expanding. Scientists worked out roughly how large any single structure should be allowed to grow before it starts breaking the smoothness the model requires. That number became something like a speed limit sign posted along the highway of cosmic history, a line nothing was supposed to cross. Here is where the story turns uncomfortable. Structures have already been found crossing that line, some of them by a wide margin, and they were found well before Webb ever pointed its mirror toward the earliest galaxies. To understand exactly how disturbing that is, we first need to see the actual number scientists calculated, and just how confidently they expected nothing in the sky to ever beat it. Somewhere in a research paper, tucked between charts and equations, sits a single number that quietly became one of the most important thresholds in modern cosmology. Scientists calculated it by combining three simple ingredients: how old the universe is, how fast light travels, and how quickly everything keeps expanding away from everything else. Put those three together, and you get a rough answer to a very specific question. How large could any coherent structure possibly grow, given the time available since the beginning? The logic behind this ceiling is easier to picture than the math behind it. Gravity needs time to pull matter together across a distance, and nothing, not even gravity's influence, can act faster than the speed of light allows information to travel. Add in the fact that the universe itself keeps stretching, carrying regions of space apart from each other, competing directly against gravity's pull. Balance those two forces against the roughly 13.8 billion years the universe has existed, and you land on a ceiling for structure size. Scientists set that rough ceiling at approximately 1.2 billion light-years across. To most people, a billion light-years sounds unimaginably huge already, so a ceiling that size might not sound restrictive at all. But compared to the true scale of the observable universe, 1.2 billion light-years is closer to a modest neighborhood than an entire city. Picture a rope that has had roughly 13.8 billion years to grow, but the growth is fighting against a treadmill that keeps stretching the rope apart even while it grows. That is the tug of war setting this ceiling, and it explains why anything found sprawling far past that number deserves serious scrutiny rather than a passing shrug. This ceiling was never meant to be an unbreakable law of physics carved in stone. It was a statistical expectation, a strong prediction based on how structure is supposed to behave if the standard model of cosmic growth holds up. Finding one structure slightly above that line might be written off as a rare, unlucky fluke, since even ordinary chance produces occasional outliers. Finding several such structures spread across different surveys and different corners of the sky starts to look like something else entirely. One outlier crossing the line is unusual but forgivable, statistically speaking. A pattern of outliers crossing that same line again and again across separate surveys run by separate research teams over the course of a couple decades tells you the odds you started with might simply be wrong. That is the exact position cosmologists found themselves in once the giant structures started piling up, one after another, each one harder to dismiss than the last. And that is exactly what happened. Long before the James Webb Space Telescope ever entered the picture, astronomers using very different instruments, including ground-based surveys mapping bursts of high-energy light from dying stars, had already stumbled onto something that blew straight past the calculated ceiling. It did not creep over the line by a small, forgivable margin either. It obliterated it, forming a wall of galaxies so enormous that some researchers still argue about whether it should even count as a single connected structure at all. In 2013, a team of astronomers mapping short, violent bursts of high-energy light across the sky noticed those bursts were not scattered randomly at all. They clustered together, tracing the outline of something almost too large to comprehend. When the mapping was finished, they had charted a wall of galaxies, stretching roughly 10 billion light-years across, a structure now known as the Hercules Borealis Great Wall, and to this day, it remains one of the largest single structures ever identified in the observable universe. Stop and actually sit with that number for a moment. The theoretical ceiling calculated in the last chapter put a rough limit on coherent structure at about 1.2 billion light-years. This wall stretches roughly 8 times past that limit. It is not a narrow miss or a borderline case that reasonable scientists could argue away as measurement noise. It is a structure so large that light itself, moving at the fastest speed anything in the universe can travel, would need about 10 billion years just to cross from one end of it to the other. Here is what makes it even stranger. This is a confirmed observation, backed by multiple independent studies that mapped the positions of those high-energy bursts and consistently found the same clustering pattern, concentrated in the same region of sky. The wall is real. The genuine debate scientists are still having centers entirely on what it means that something this size managed to form at all, given how much time gravity actually had to work with. Some researchers have pushed back on one narrow point, arguing about whether every burst in the mapped cluster truly belongs to a single connected structure, or whether astronomers are looking at several separate clumps that happen to overlap when viewed from our vantage point. That is a fair scientific debate, and it remains genuinely unresolved. But even the more conservative estimates of the wall's true size still land well past the ceiling the Standard Model predicted, which is exactly why this discovery could not simply be waved away. Picture trying to build a structure 10 billion light-years long, using only gravity, working patiently over the entire history of the universe, while the universe itself keeps stretching space apart the whole time. That is like trying to knit an enormous blanket while someone continuously pulls new thread off both of your needles as you work. The math says it should not be possible, at least not within the timeline the Standard Model allows. Yet there the wall sits, mapped and confirmed and stubbornly refusing to disappear. This wall was the first real crack in the ceiling, but it was not actually the first one scientists had ever spotted. An earlier, somewhat smaller, Great Wall had already raised eyebrows years before Hercules Borealis was even mapped, quietly hinting that something about the universe's growth timeline might not add up. Understanding that earlier warning sign makes the more recent discoveries hit even harder. Years before astronomers charted the 10 billion light-year wall, a smaller cousin had already been sitting in the data, largely overlooked by anyone outside the field. In 2003, a team studying a massive survey of galaxies identified a filament of galaxies stretching roughly 1.4 billion light-years across, later nicknamed the Sloan Great Wall after the survey that found it. At the time, it was the largest structure ever confirmed in the observable universe, and it already sat right at the edge of what the theoretical ceiling allowed. This wall did not shatter expectations the way its larger cousin eventually would. It sat close enough to the calculated limit that many scientists treated it as an edge case, a structure worth noting, but not one that demanded the Standard Model be rewritten. Think of it as a single yellow warning light on a dashboard rather than a full alarm. Something was worth watching, but nobody was panicking yet, since one borderline case could still be explained away as an unusually lucky roll of cosmic dice. Confirmed by repeated survey data and cross-checked by independent research teams, the Sloan Great Wall was never seriously in doubt as a real, physical structure. The open question was always about interpretation rather than existence. Was this filament simply an extreme but expected outlier, the kind any sufficiently large survey would eventually turn up by chance? Or was it an early hint of a much bigger pattern, still waiting to be uncovered in deeper, wider surveys that had not been run yet? For close to a decade, most cosmologists leaned toward the cautious explanation. Big surveys covering enormous volumes of space will occasionally find rare, oversized structures purely by chance. The same way, flipping a coin 1,000,000 times will occasionally produce an unlikely streak of the same result in a row. One warning light, on its own, rarely justifies tearing apart a well-tested model that has succeeded at nearly everything else it was asked to predict. There was also a quieter reason scientists stayed cautious. The Sloan Great Wall sat relatively close to us in cosmic terms, meaning its light had not traveled anywhere near as far back in time as the structures still waiting to be discovered. A single oversized structure found nearby says less about the early universe's growth rate than a similar structure found much farther away at a much younger cosmic age. Distance, once again, mattered just as much as size. Then the Hercules Corona Borealis Great Wall showed up, obliterating the ceiling by a much wider margin than the Sloan Great Wall ever had. Suddenly, that single yellow warning light from 2003 looked a lot less like an isolated fluke and a lot more like the opening note of a pattern. And the pattern was only getting started, because the very next major discovery would not come from a survey of galaxies at all. It would come from something stranger, hidden inside the flickering light of objects sitting even farther away than any wall of galaxies charted so far. In 2021, a researcher combing through survey data noticed a pattern that had been sitting there unnoticed for years, curled across the sky like a faint brushstroke nobody had bothered to connect. She was not looking for a giant wall of galaxies. She was studying the light of extremely distant, extremely bright objects, and buried in that data was the outline of an arc of galaxies stretching an almost unbelievable 3.3 billion light-years from end to end. This arc did not announce itself the way a bright object normally would. It emerged only after careful statistical work revealed that galaxies and gas clouds along a specific curved path were sitting closer together and more densely packed than random chance should ever produce. Once the pattern was mapped out fully, it traced a graceful, sweeping curve across a huge stretch of the sky, which is how the discovery earned its name, the Giant Arc. Here is why this discovery landed so hard among cosmologists. The arc sits roughly 9.2 billion light-years away, meaning the light reveals what that region of space looked like when the universe was less than half its current age. A structure that size, at that distance, sits well beyond what the theoretical ceiling from earlier chapters allows for a coherent, connected structure. It joined the growing list of giant walls that simply should not have had enough time to form. What makes the Giant Arc different from the walls discussed earlier is not just its shape. It was found using an entirely separate technique, studying distant background light rather than directly counting and mapping galaxies the way earlier Great Wall surveys had. Two completely different methods, aimed at two completely different regions of sky, kept landing on the same uncomfortable conclusion. Something out there keeps organizing itself into structures far larger than the rulebook allows. To grasp the scale here, consider that 3.3 billion light-years is roughly a third of the total distance back to the very beginning of the observable universe. Very few individual objects or structures in astronomy get measured in fractions of the entire cosmos. Most galaxies, even large ones, barely register as a rounding error against that kind of yardstick. An arc spanning a meaningful slice of the whole observable universe is a different category of object altogether. The scientist who discovered the arc did not stop looking once the discovery was published. She kept combing through the same region of sky, hunting for anything else hiding in that same slice of ancient light. What she found next would turn one strange structure into two, sitting almost impossibly close to each other, and that pairing is what truly turned this from an interesting anomaly into a full-blown mystery worth investigating at every level. Before we get to that second structure, it helps to understand exactly how a scientist manages to find something like a 3 billion light-year arc hidden inside data that was never designed to map giant structures in the first place. The trick involves treating some of the brightest objects in the universe as flashlights instead of destinations. Some of the brightest single objects in the observable universe are not stars or galaxies at all. They are quasars, extremely distant, extremely energetic cores of galaxies, powered by an enormous amount of material falling toward a massive black hole at their center. Quasars shine with such intensity that their light remains detectable across billions of light years, making them useful for something far beyond simply studying the quasars themselves. Some of these objects outshine their entire host galaxy combined, which is exactly what makes them visible from such staggering distances in the first place. Here is the clever part. As light from a distant quasar travels toward us, it does not arrive untouched. It passes directly through everything sitting in its path, including thin clouds of gas, faint filaments of galaxies, and other material scattered along that billions of light-year journey. Each time that light passes through matter, tiny fingerprints get stamped into it, subtle dips and gaps in the light spectrum that reveal exactly what the light passed through on its way to us. Astronomers read those fingerprints the way a detective reads footprints left in mud. By studying the spectrum of light from many quasars scattered across a region of sky, scientists can reconstruct an outline of invisible material lying between us and those distant beacons, without ever directly photographing that material at all. It is a bit like mapping the shape of a hidden object by studying the shadow it casts across dozens of different flashlight beams instead of turning on the room lights and looking directly at it. This technique, called quasar absorption mapping in scientific circles, gave astronomers a completely new tool for finding structure that ordinary galaxy surveys might miss entirely. Some material sitting between us and a distant quasar is too faint, too spread out, or too gas-rich to show up clearly in a standard photograph of the sky. But it still leaves a fingerprint in the light passing through it, and that fingerprint is more than enough to reveal size, shape, and rough location. Building one of these maps takes patience. Researchers gather the spectrum of light from dozens of separate quasars scattered across the same general patch of sky, then compare the fingerprints from each one, searching for spots where several beams show the same telltale dips at the same rough distance. Only when multiple independent beams agree does a real structure start to take shape on the map, rather than random noise that happened to line up by coincidence. That layer of cross-checking is exactly why scientists trust what this method reveals. This is exactly the method that revealed the giant arc in the previous chapter, and it is the same method that would soon reveal something even stranger sitting nearby. Because once researchers realized how powerful this flashlight technique really was, they turned it toward the same general region of sky again, half expecting to find nothing new. What they found instead reopened the entire mystery, and this time the structure they uncovered was not shaped like an arc at all. It was shaped like a ring. 3 years after the giant arc made headlines, the same researcher went back to the same patch of sky and found a second impossible structure sitting almost in plain sight. Announced in 2024, this new discovery traced out a striking circular pattern of galaxies stretching about 1.3 billion light-years across, big enough on its own to sit right at the edge of the theoretical ceiling described several chapters ago. Astronomers gave it a fittingly simple name. They called it the Big Ring. Unlike a loosely connected filament or a sprawling wall, the Big Ring forms a strikingly clean, almost deliberate-looking circular shape when mapped out. That circular outline is part of what made the discovery so unsettling to the researchers involved. Random clumping produced by ordinary gravity tends to create messy, irregular shapes, filaments with branches, walls with ragged edges, clusters with uneven clumps scattered throughout. A smooth, closed loop is a very different kind of pattern to stumble across by pure accident. Confirmed through the same rigorous quasar absorption mapping described in the last chapter, the Big Ring is not a disputed claim or a statistical illusion cooked up by wishful pattern matching. Multiple background quasars, showed consistent fingerprints tracing the same circular outline at the same rough distance, which is the exact kind of cross-checked evidence that gives a discovery like this real scientific weight rather than internet speculation status. Peer review took its usual careful path before this discovery reached the public. Other astronomers checked the data, tested alternate explanations, and looked for reasons the pattern might be an accident of how the quasars happen to be distributed. None of those checks made the ring disappear. It held up, which is exactly the kind of scrutiny a claim this dramatic needs to survive before anyone should take it seriously. Here is the detail that made jaws drop across the astronomy community. The big ring sits at almost exactly the same distance from us as the giant arc, roughly 9.2 billion light-years away, occupying a nearly overlapping region of sky. Two separate, enormous, rule-breaking structures, discovered years apart using the same method, sitting practically next door to each other in the same slice of cosmic history. That is not the kind of coincidence scientists brush off without a second look. Some researchers have proposed the ring might actually be a projection, a three-dimensional spiral or shell-shaped structure that only appears circular because of the angle we happen to be viewing it from, similar to how a spinning coin can look like a perfect circle from one angle and a thin line from another. That idea remains a genuine, unresolved hypothesis rather than a settled answer, and it is one of several competing explanations still being debated. Whatever the ring truly is in 3 dimensions, its sheer existence next to the giant arc raised an uncomfortable question that nobody could ignore for long. Was finding 2 record-breaking structures in practically the same spot really just an extraordinary coincidence? Or was something deeper connecting them, something that would force cosmologists to rethink individual structures and the entire map of that region of the ancient universe together? Lay the giant arc and the big ring on top of the same 3-dimensional map of the sky, and something deeply strange jumps out immediately. Both structures sit at almost identical distances from us, both occupy overlapping patches of sky, and both were uncovered using the exact same quasar absorption technique. 2 of the largest structures ever confirmed in the observable universe are practically neighbors, separated by only a small angular distance when viewed from where we sit. Statisticians have a specific way of testing whether something like this could plausibly happen by pure random chance. Researchers ran calculations estimating the odds of 2 structures this large appearing this close together at this same rough distance, purely as a random coincidence produced by ordinary galaxy clustering. The odds came back small enough to make most scientists uncomfortable, the kind of result that normally pushes a claim from curious anomaly toward genuine scientific mystery deserving serious follow-up. Here is a comparison that helps put the improbability into perspective. Imagine flipping a coin and getting heads 10 times in a row purely by chance. Unlikely, but not impossible, and it happens somewhere in the world fairly often given how many people flip coins every day. Now imagine flipping heads 20 times in a row instead. That is roughly the flavor of improbability researchers were staring at when they calculated the odds of the arc and the ring appearing together by pure random accident. None of this proves the 2 structures are physically connected, reaching out and touching each other across space the way 2 neighboring countries share a border. They could still be entirely separate objects that simply happen to occupy a similar volume of the ancient universe, an outcome that remains possible even if it feels increasingly unlikely. Genuine open mystery is the honest label here, not a confirmed connection and not a debunked coincidence either. Scientists have not settled this question, and anyone claiming certainty in either direction is overstating the evidence. What nobody disputes is the bigger pattern building across this entire investigation, a 10 billion light-year wall, a smaller wall that hinted at trouble years earlier, an arc spanning nearly a third of the observable universe, a ring sitting almost on top of that same arc, 4 separate discoveries, 4 separate research efforts, and every single one landing in the same uncomfortable territory beyond what the standard model was ever supposed to allow. The pattern itself is becoming as important as any single structure inside it. But identifying a pattern is not the same as explaining it, and the ring in particular raises a question none of the earlier structures ever forced scientists to confront quite so directly. What does it actually mean for a structure to form a circle in the first place? Because a circle this size is not just big. It is organized in a way that plain, random gravitational clumping struggles to produce on its own, and that detail opens up an entirely new branch of the mystery. Nobody believes there is a literal, physical loop of galaxies floating in space, curved like a giant hoop someone tossed across the universe. That image, while dramatic, is not what scientists mean when they describe the Big Ring, and clearing up that confusion matters before the mystery can be taken seriously. What astronomers actually detected is a pattern in the data, a circular arrangement of galaxies and gas when mapped onto the sky from our particular point of view. That distinction opens up several competing explanations, each one still very much on the table. One idea suggests the ring could be a two-dimensional slice through a three-dimensional shape, something like a spiral, a shell, or a bubble, that only looks like a perfect circle because of the specific angle from which we happen to be observing it. Under this explanation, the ring is real, but its true geometry in 3 dimensions is something scientists have not fully pinned down yet. A second idea reaches back to the earliest moments after the beginning of everything. Sound waves rippled through the hot, dense material filling the newborn universe, leaving behind faint, roughly spherical patterns in how matter eventually clumped together, patterns baked into the cosmos, long before galaxies ever existed. Some researchers wonder whether the Big Ring could be a rare, unusually large, or unusually well-preserved version of that ancient sound wave pattern, still faintly outlined in how galaxies are distributed today. Neither of these explanations is confirmed. Both remain genuine working theories, actively debated inside the research community, with new papers testing each possibility against the data as it improves. That distinction matters enormously here. Confirmed observation says a real, circular pattern of galaxies and gas exists, cross-checked and repeatedly verified. What causes that pattern to exist, and whether it truly counts as a single connected object rather than an alignment of separate pieces, remains an open scientific question without a settled answer. There is also a third possibility scientists have not ruled out, one far less exotic than sound waves from the beginning of time. The ring could simply be an unusually striking alignment of several unrelated structures that happen to overlap when viewed from our specific vantage point in space, without being physically connected to each other at all. Untangling that possibility from a genuinely connected structure requires more data, more distant background quasars to check, and more time. Whatever the ring truly represents, it made one thing painfully clear. The standard model of gradual, gravity-driven growth was already struggling to explain giant walls and arcs. A perfectly organized ring added an entirely new layer of difficulty on top of an already uncomfortable size problem. And while astronomers were still debating what to make of these enormous ancient structures, an entirely different telescope was quietly preparing to attack the same mystery from a completely different angle, hunting this time for the very first structures ever assembled rather than for giant structures scattered billions of light years away. While one group of scientists was busy mapping giant arcs and rings scattered across billions of light years of the ancient sky, a different approach was quietly taking shape. Rather than search for oversized structures at a medium point in cosmic history, researchers using the James Webb Space Telescope decided to aim straight at the beginning itself, hunting for the very first clumps of galaxies ever assembled, sitting right at the dawn of cosmic time. It was a bold shift in strategy, and it came with real risk attached, since a hunt this ambitious could easily have turned up nothing at all. This shift in strategy mattered enormously because it created a much sharper test of the standard model than any single giant wall ever could. A wall found partway through cosmic history had billions of years to form, even if that number still fell short of what its true size demanded. A structure found at the very beginning has almost no time cushion left to work with at all. If something organized and massive turns up there, the standard model does not just look strained, it looks cornered. Researchers targeted a specific stretch of cosmic history for this hunt, sometimes nicknamed Cosmic Dawn, the earliest few 100 million years after the beginning, when the first stars and galaxies were only just beginning to ignite. Under the standard model, this period should look sparse and disorganized, filled with small, scattered, still-forming galaxies, rather than anything resembling a bound, structured cluster. It is supposed to be the toddler phase of the universe, long before any real neighborhoods had time to develop. Finding nothing but scattered infant galaxies in that era would have confirmed the standard model beautifully, adding one more successful prediction to its already impressive track record. That is not what happened. Instead, tucked behind a massive foreground cluster of galaxies, acting as a natural cosmic lens, researchers spotted something that looked disturbingly like an organized, gravitationally bound group of galaxies already coming together, sitting at a point in cosmic history where nothing that organized was supposed to exist yet. This single discovery threatened to do something the giant walls, arcs, and rings never quite managed on their own, because it was found at the very edge of observable time, at the very dawn of structure formation itself. It left almost no room for the usual defense of simply saying more time was still available somewhere. There was no more time available. This was as early as it gets, and something was already there waiting. Before diving into exactly what researchers found hiding behind that foreground cluster, it helps to understand the remarkable trick that let them see it in the first place. Because spotting something this faint, this old, and this far away required more than just a powerful mirror. It required borrowing gravity itself as a magnifying tool, bending and amplifying ancient starlight in ways that turned an ordinary foreground galaxy cluster into one of the most powerful telescopes in existence. Ordinary telescopes gather light using mirrors or lenses built by human hands. The trick behind this next discovery uses a very different kind of lens, one built entirely out of gravity itself. When a massive foreground cluster of galaxies sits directly between us and something much farther away, its enormous gravitational pull bends the fabric of space around it, warping and magnifying any light passing nearby on its way toward us. Astronomers call this effect gravitational lensing, and it turns an ordinary cluster of galaxies into a natural magnifying glass. Here is why that trick matters so much for spotting the earliest structures in the universe. Objects from the dawn of cosmic time are almost unimaginably faint by the time their light reaches us, stretched, dimmed, and scattered across billions of light years of expanding space. Even the most powerful mirror ever launched into orbit struggles to detect some of these targets directly. But point that same mirror through a massive foreground cluster, acting as a gravitational lens, and suddenly faint, distant light gets stretched, brightened, and magnified before it even reaches the telescope. Researchers used exactly this technique, aiming the James Webb Space Telescope through a well-known foreground cluster of galaxies to study a patch of extremely distant, extremely faint light behind it. The foreground cluster's gravity did much of the heavy lifting, magnifying that ancient light several times over before the telescope's own sensitive detectors ever captured it. Without that natural boost, some of the faintest galaxies in this discovery likely would have remained completely invisible, hidden below the detection threshold of even the most advanced instrument ever built. This combination, an extremely sensitive infrared telescope paired with a naturally occurring gravitational magnifying glass, is what finally made it possible to study individual galaxies from the earliest few 100 million years of cosmic history in real detail, rather than just as faint, unresolved smudges of light. Instead of one blurry blob, researchers could count individual galaxies, estimate their masses, and measure how tightly they clustered together in space, all from a target sitting near the very edge of the observable universe. That level of detail is exactly what revealed something researchers were not fully prepared for. Behind that foreground lens, in that faint, magnified, ancient light, sat not just one or two young galaxies scattered randomly across the field. It was a cluster, already gathering into a bound, gravitationally connected group, sitting at a point in cosmic history so early it barely qualifies as a percentage of the universe's current age at all. What researchers found in that lensed field turned out to be the very discovery teased back in the opening chapter of this story. And now, with the full context of the Standard Model, the theoretical ceiling, and the giant structures already found finally laid out, its true weight becomes impossible to ignore. It is time to look directly at what was actually hiding behind that gravitational lens, and just how early it truly formed. Hiding behind the gravitational lens described in the last chapter sat a tight group of at least 8 separate galaxies, all clearly bound together by their shared gravity rather than simply drifting past each other by coincidence. Researchers nicknamed the discovery a preview of a mature galaxy cluster, and that word choice was deliberate. What they were looking at behaved like the seed of something enormous, caught in the act of coming together far earlier than anyone expected to catch it. The timestamp on this discovery is what makes it so hard to explain away. As established earlier, the light reaching the telescope left these galaxies roughly 650 million years after the beginning of everything, meaning this group had already begun clumping together while the universe was still less than 5% of its eventual age. Compare that to a fully grown, well-studied cluster nearby, the kind that took the vast majority of cosmic history to assemble, and the mismatch becomes obvious immediately. Researchers estimate that a bound group this size, this early, is likely the ancestor of something resembling the massive galaxy clusters we observe much closer to home today, systems that can stretch several million light-years across and contain hundreds of individual galaxies once fully mature. Finding the seed of one of those giants already forming at cosmic dawn is like discovering a fully fertilized egg sitting in a nest that, according to the calendar, was supposedly still empty. What makes this discovery different from the giant walls, arcs, and rings covered earlier in this story is timing rather than size. Those structures were large but appeared later in cosmic history, giving the Standard Model at least some stretch of time to work with, even if that stretch still fell short. This cluster appeared at the very earliest point scientists can currently observe at all. There is no earlier cosmic era left to point to and say, just wait, there was more time than it looks like. This is as close to the starting line as observation currently reaches, confirmed by careful gravitational lens modeling and cross-checked against the foreground cluster's own well-studied properties. This newborn cluster is not a fringe claim floating on shaky data. It has been through peer review, scrutinized by independent researchers, and it continues to hold up under further study. The debate here, much like with the giant walls before it, is not whether the observation is real. It is about what a discovery this early actually means for a model that insists nothing should look this organized yet. That single word, organized, is doing a lot of heavy lifting in this story, and it deserves closer attention, because the real problem with this cluster is not simply that it exists too early. It is that building something this coordinated, this quickly, using only the patient pull of gravity working through the Standard Model's rulebook, may be close to a genuine contradiction rather than just an uncomfortably tight timeline. Imagine planting a handful of seeds in freshly turned soil, walking away for a single afternoon, and returning to find a fully grown forest standing where the seeds had been. Tall trees, tangled root systems, layers of undergrowth, a functioning ecosystem, all of it complete, all of it in the space of a few hours. Anyone witnessing that would immediately suspect something about their understanding of how forests grow was deeply wrong. That is roughly the scale of the problem this newborn galaxy cluster presents to cosmologists. Under the Standard Model, building a bound group of galaxies requires a very specific sequence of events, and each step in that sequence takes real time to unfold. Dark matter first needs to gather into a dense enough clump to create a gravitational trap. Ordinary matter then needs to fall into that trap and begin condensing into individual galaxies. Those galaxies then need enough additional time to notice each other's gravity, begin orbiting a shared center, and settle into something recognizable as a bound cluster rather than a loose, temporary crowd. Every one of those steps takes a meaningful chunk of cosmic time on its own, and the Standard Model's usual predictions stack those steps up to a timeline stretching well beyond the 650 million years available in this case. Researchers running simulations of typical cluster formation consistently find that assembling something this massive, this early, should be extraordinarily rare under standard assumptions, if it is possible at all within the model's normal range of outcomes. That word, rare, is doing important work here too, and it deserves an honest explanation. Rare does not automatically mean impossible. Even a well-tested model built on solid observational evidence allows for occasional statistical outliers, unusual regions of the early universe where matter happened to clump slightly faster than average, purely by chance. One early cluster, taken entirely alone, might squeeze through as an extreme but technically permitted exception rather than outright proof the model is broken. A single unusual case, taken alone, would not force anyone to rewrite a model that has otherwise proven itself again and again across decades of testing. The trouble is that this cluster is not standing alone in the data. It joined an already growing pile of giant walls, oversized arcs, an unexplained ring, and now a full-sized cluster preview showing up right at the very edge of observable time. Confirmed observation keeps landing outside the boundaries the Standard Model was built to allow, again and again, across different techniques, different research teams, and different corners of the sky. At what point does a string of rare exceptions stop looking like bad luck and start looking like a pattern demanding a real explanation? That exact question became even sharper once researchers turned their attention away from clusters made of many separate galaxies and instead zoomed in on individual galaxies that appeared, on their own, to be carrying far more mass than the timeline of the early universe should have allowed them to build. In 2023, a team analyzing early images from the James Webb Space Telescope flagged 6 candidate galaxies that immediately triggered alarm bells across the astronomy community. These galaxies appeared to date from the first several 100 million years after the beginning, and yet their measured brightness suggested they had already packed together an amount of stellar mass that seemed almost impossible to build in that shorter window of time. One of the most extreme candidates in that group appeared to hold a mass roughly equal to our entire home galaxy, fully packed with stars, at a point when the universe was less than 3% of its current age. Researchers only half joked at the time that finding a galaxy this developed this early felt like finding a fully staffed office building standing in a field where, according to every planning document, construction had not even begun. The core issue researchers pointed to involves something called the baryon budget, a fancy way of describing the total amount of ordinary matter available to form stars within a given region of the early universe. Standard cosmology places a rough ceiling on how much of that available matter could realistically convert into visible stars within the first few 100 million years, since star formation itself takes time, and converting raw gas into finished, shining stars is not an instantaneous process. Several of these 6 original candidate galaxies appeared to blow directly past that ceiling, showing signs of holding more stellar mass than models expected the entire surrounding region to have been able to supply in the time available. If even 1 or 2 of these extreme cases held up under closer scrutiny, it would represent a direct challenge to core assumptions about star formation efficiency in the earliest galaxies, not just a challenge about structure size, the way the giant walls and rings had been. This discovery landed like a genuine jolt through the field, specifically because it did not rely on some indirect statistical mapping technique or a rare, hard-to-interpret alignment of galaxies. These were individual, directly imaged objects, each one bright enough and clear enough to measure with reasonable confidence using standard astronomical tools. A challenge this direct is much harder to wave away as a fluke of data processing or an unlucky coincidence buried in a complicated survey. Confirmed observation established that these 6 objects were real, sitting exactly where the data placed them, glowing with exactly the brightness researchers measured. What remained genuinely uncertain, and still does for a portion of these cases, was the interpretation of that brightness, specifically how much of it truly came from mature stars packed into each galaxy, and how much might be explained by something else entirely hiding in plain sight. That distinction turned out to matter enormously, and untangling it required a much closer, more careful look than the first alarming headlines ever gave it. News coverage at the time leaned heavily into the most dramatic framing available, and headlines calling these objects universe-breaking spread quickly across the internet. Scientists themselves were more careful with their language from the very beginning, describing the findings as a serious tension worth investigating rather than a confirmed crisis. That distinction between public excitement and careful scientific caution would matter a great deal once follow-up studies began rolling in. Suppose, for a moment, that these giant structures and impossibly massive early galaxies genuinely cannot be explained within the standard model, no matter how researchers massage the numbers. What then? This is where cosmology stops sounding like settled science and starts sounding like a genuine frontier again, because several serious, competing theories are already being explored to explain a universe that grew up faster than expected. One leading idea involves dark matter behaving slightly differently than the simplest version of the standard model assumes. If dark matter clumps together a bit more efficiently, or interacts with itself in ways not yet fully understood, it could build gravitational scaffolding faster than current simulations predict, giving ordinary matter a head start on forming large structures. This remains a genuine, actively researched theory rather than a confirmed replacement for the existing model, though it is one of the most discussed options on the table. A second idea reaches even further back, proposing that primordial black holes, hypothetical black holes, formed directly from the extreme density of the very early universe rather than from a collapsing star, might have acted as seeds for structure formation. If enough of these ancient black holes existed early on, their gravity could have kick-started the clumping process well ahead of schedule, giving both galaxies and clusters a considerable jump start. This idea remains speculative and unconfirmed, but it has gained renewed attention specifically because of these early, oversized discoveries. A third possibility involves modified gravity, the idea that gravity itself might behave slightly differently across truly enormous distances and timescales than Einstein's well-tested equations currently describe. Modified gravity theories are far from mainstream consensus, and most researchers remain skeptical given how well standard gravity has performed in nearly every other test scientists have thrown at it. Still, an unresolved anomaly this persistent is exactly the kind of evidence that keeps alternative gravity theories from being dismissed outright. A fourth option focuses on dark energy, the mysterious force driving the universe's accelerating expansion. Some researchers wonder whether dark energy's strength or behavior might have shifted over cosmic history in ways the simplest version of the standard model does not currently account for, subtly altering how fast structure could form during the universe's earliest chapters. Like the other theories here, this remains an open avenue of active research rather than an accepted conclusion. Every explanation on this list shares one important trait: none of them has been confirmed. Each represents a genuine, actively debated theory, competing for attention inside a field that takes its evidence seriously and does not hand out major revisions lightly. Notice also that none of these 4 ideas are small tweaks. Each one would reshape a fundamental piece of how scientists understand reality itself, which is exactly why researchers are moving carefully rather than rushing to declare a winner. Before any of these ideas gain real traction, though, scientists have to rule out something far less exciting and far more likely to be the actual explanation for at least some of these startling discoveries. Extraordinary claims in astronomy almost always get tested against ordinary, unglamorous explanations before anyone seriously entertains rewriting the textbooks. This step is not optional, and skipping it would be bad science. Before a giant structure or an impossibly massive early galaxy gets treated as evidence, the standard model is broken. Researchers have to rule out simpler, far less dramatic possibilities first, no matter how tempting the exciting explanation might feel. The first suspect is almost always measurement error. Estimating the distance and age of an extremely faint, extremely distant object is genuinely difficult work, involving careful analysis of stretched, weakened light gathered from the very edge of what current instruments can detect. Small errors in that analysis can shift an object's estimated age or distance significantly, sometimes enough to turn a borderline case into a headline-grabbing anomaly or an anomaly into an unremarkable, fully explainable object. A second major suspect involves black holes hiding inside these apparently oversized galaxies. An extremely active black hole devouring surrounding gas at the center of a young galaxy can produce enormous amounts of light and heat, the light that can easily be mistaken for the glow of an enormous population of mature stars, if researchers are not careful separating the two sources. Several of the 6 massive galaxy candidates discussed earlier turned out, after closer study, to have their apparent stellar mass reduced once researchers accounted for exactly this kind of contamination. Dust presents a third complication. Clouds of dust scattered throughout a young galaxy can absorb and redirect light in ways that confuse mass estimates, sometimes making a smaller, more ordinary galaxy appear artificially larger or more massive than it truly is once its light finally reaches our instruments. Accounting properly for dust requires careful modeling, and getting that modeling wrong can inflate an object's apparent size well beyond its actual scale. None of these boring explanations have managed to fully dissolve every anomaly on the table, and that detail matters enormously. Some of the 6 original massive galaxy candidates saw their estimated mass revised downward substantially once follow-up analysis accounted for black hole contamination and dust, bringing them back within range of what the standard model allows. Others held up even after that closer scrutiny, keeping at least part of the original mystery firmly alive rather than resolving it entirely. This is exactly how healthy science is supposed to work, testing the mundane explanations first and only taking the extraordinary ones seriously once the ordinary options run out. It is also worth noting that ruling out a boring explanation for one object says nothing about the next. Every single case on this growing list has to be checked individually on its own evidence, which is slow, careful work compared to the instant certainty a dramatic headline offers. That process was still actively unfolding when researchers turned to a more powerful tool capable of settling many of these lingering disputes directly, a tool that could measure distance and composition with far greater precision than the original Discovery images ever could. Snapping a picture of a distant galaxy is only the first step in understanding it. To pin down an object's true distance, age, and composition with real confidence, astronomers turn to a technique called spectroscopy, which splits an object's light apart into its individual component colors, revealing detailed fingerprints about exactly what that light passed through and exactly how far it has traveled. This is a far more precise tool than the imaging techniques used to first flag many of these unusual candidates. Once researchers pointed detailed spectroscopic instruments at several of the original massive galaxy candidates, the results split cleanly in 2 directions. Some candidates held up beautifully under the more precise measurement, confirming both their extreme distance and their surprisingly large mass, keeping the original mystery fully intact and demanding a genuine explanation. Other candidates did not hold up nearly as well, with more precise data revealing lower masses, closer distances, or significant light contamination from an active black hole that imaging alone had failed to properly separate out. This split result is actually the healthiest possible outcome for the field, even though it makes for a messier headline than a single dramatic yes or no answer. It shows the scientific process working exactly as intended, correcting itself where correction was needed while preserving the genuinely strange cases that still deserve serious attention. Roughly half of the 6 original massive galaxy candidates saw their status meaningfully revised after spectroscopic follow-up, while the rest remained stubbornly, legitimately anomalous. The giant structures covered earlier in this story, the walls, the arc, and the ring, have faced a similar layered process of scrutiny, though the tools used to check them differ from the ones used on individual galaxies. Independent research teams have re-examined the underlying survey data, tested alternate statistical methods, and searched for reasons the patterns might be artifacts of how the original data was collected. So far, none of those checks have made the giant structures disappear the way some of the massive galaxy candidates ultimately did. That distinction matters enormously for how seriously this entire investigation should be taken. This is not a story about one dramatic claim that fell apart under scrutiny, the kind of finding that quietly disappears from headlines a year later. It is a story about a mixed, evolving body of evidence, where some claims got walked back through careful, honest science, while others have survived every single test thrown at them so far, refusing to simply vanish the way a data error normally would. With the boring explanations properly sorted from the genuine anomalies, one question remains standing at the center of everything covered so far. Are these surviving, confirmed anomalies simply an unusually unlucky cluster of rare statistical outliers, explainable within the normal range of what the standard model allows if you wait long enough for the numbers to average out? Or has enough evidence piled up now to call this something else entirely, a genuine, structural problem sitting at the heart of modern cosmology? Scientists have a formal way of measuring how surprised they should be by a result, and it comes down to a simple question. If the standard model is completely correct, how often would you expect to stumble across something this extreme purely by chance? A result that would only show up once in 100 tries under normal conditions is interesting but not necessarily alarming. A result that should only show up once in many thousands of tries starts to demand a real explanation. Individually, each structure covered in this story might have squeezed through as a rare, tolerable outlier. One oversized wall, on its own, could plausibly be an unlucky roll of cosmic dice, since even a fair coin occasionally produces a surprising streak. That defense gets weaker with every additional structure added to the pile, though, because the odds of an honest model producing this many separate, extreme outliers in this short a span of research keep shrinking with each new confirmed case. Consider the full list assembled across this story so far. A wall stretching 10 billion light-years, blowing past the theoretical ceiling by a wide margin. An earlier wall that hinted at the same problem years before. An arc long enough to stretch across close to a third of everything we can ever observe. A ring sitting almost directly on top of that same arc, defying easy odds of coincidence. A bound cluster forming at the very edge of observable time when almost no cosmic time cushion remained. And a handful of individual galaxies that appeared to weigh far more than their age should have allowed, some of which survived every round of careful scrutiny thrown at them. Taken together, this is no longer a single anomaly asking to be explained away. It is a pattern spread across multiple independent techniques, multiple research teams, and multiple separate regions of the sky, all pointing in the same uncomfortable direction. That kind of convergence, arriving from different angles rather than a single flawed study, is exactly the kind of evidence that legitimately shifts scientific opinion over time, even inside a field as careful and conservative as cosmology. None of this amounts to proof that the standard model is wrong, and responsible scientists are careful to say so clearly. It remains entirely possible that better data, more precise instruments, and larger survey volumes will eventually smooth out every one of these apparent tensions, folding them quietly back into the range the model always allowed. That outcome remains genuinely on the table and dismissing it outright would be just as unscientific as declaring the model broken today. What is no longer reasonable is treating every single one of these findings as an isolated curiosity with no connection to the others. The pattern itself has become data, worth studying on its own terms, and that shift in framing opens the door to an even stranger question, one that reaches back past every galaxy, past every giant wall, all the way to the first fraction of a second after the universe began. Every giant structure in this story eventually traces back to the same starting point, a moment scientists call inflation, an unimaginably brief period right after the beginning when the universe is thought to have expanded at a staggering rate, stretching microscopic quantum fluctuations into the seeds that would later grow into every galaxy, every star, and every giant wall discussed so far. If those original seeds were planted unevenly, everything that grew from them inherits that unevenness. Under the simplest version of inflation theory, those seeds should have been scattered fairly randomly, small and modest in scale, requiring gravity to do nearly all of the heavy lifting afterward to build anything as large as the structures covered throughout this story. That assumption is exactly what sets up the theoretical ceiling described earlier, since modest seeds need enormous amounts of time to grow into anything resembling a 10 billion light-year wall. But what if some of those original seeds were not modest at all? A small number of researchers have begun exploring whether certain variations of inflation theory could produce larger, more clustered seed patterns than the simplest version assumes, effectively giving gravity a considerable head start before the observable universe was even a fraction of a second old. Under this kind of framework, some regions of space could have arrived already, carrying the rough outline of a giant structure baked directly into their earliest starting conditions. This idea remains firmly in the territory of open theory rather than confirmed science, and it is important to be honest about that distinction. Scientists have not proven that inflation happened unevenly, and most versions of inflation theory still comfortably match the giant structures discussed throughout this story without needing dramatic modification. But an idea that was once considered a fringe curiosity has gained noticeably more attention specifically because of how consistently these oversized structures keep turning up in survey after survey, forcing even skeptical researchers to at least keep the possibility on their list of active considerations. If this theory eventually gained stronger support, the implications would reach far beyond any single giant wall or ring. It would mean the unevenness we observe today is not simply the result of gravity patiently working over billions of years. It would mean that unevenness was written into the fabric of the universe within an almost impossibly brief instant near the very beginning, before atoms, before light, before anything resembling the cosmos we recognize today had even finished forming. That possibility drags this entire investigation back to the cosmological principle introduced several chapters ago. The foundational assumption that the universe should look smooth, and even once you zoom out far enough, if the seeds themselves were never evenly scattered in the first place. That foundational assumption does not just bend under pressure from a few oversized structures. It risks buckling entirely, and the consequences of that would ripple through nearly every corner of modern cosmology, touching far more than just how astronomers explain a handful of unusually early galaxy clusters. Almost every measurement modern cosmology relies on assumes, somewhere in its underlying math, that the universe is roughly uniform once you average over a large enough volume of space. That assumption is not a minor technical footnote buried in an appendix. It is load-bearing, holding up calculations for the universe's age, its rate of expansion, the total amount of matter it contains, and the overall geometry of space itself. Weaken that assumption, and the entire structure built on top of it starts to wobble. Here is why that matters so directly for everything covered throughout this story. When astronomers calculate distances across billions of light years, they rely on formulas that assume space expands at a consistent, predictable rate everywhere, unaffected by any single region containing an oddly massive, oversized structure. If a large enough clump of matter sits in the wrong place, its extra gravity can subtly bend those calculations, throwing off distance estimates in ways that ripple outward into countless other measurements built on top of them. Even a small, systematic bias introduced this way could quietly accumulate across enough calculations to shift conclusions researchers have treated as settled for years. Consider an analogy from something far more familiar. Weather forecasters build their models assuming atmospheric patterns behave in statistically predictable ways across large regions, smoothing out small, local variations, like a single unusually hot afternoon, into a broader, reliable average. If one specific hot afternoon somehow turned out to represent an enormous, persistent shift rather than harmless local noise, every forecast built on top of the old assumption would need serious revisiting. Giant, rule-breaking cosmic structures raise a similar concern, just at a scale almost impossible to fully picture. To be clear, and this deserves real emphasis, nobody is currently claiming the cosmological principle has been disproven. Confirmed, large-scale surveys covering enormous volumes of space still show the universe smoothing out into a roughly uniform average once you zoom out far enough beyond any single structure. The open question is narrower, but still serious. Are the specific giant structures covered in this story rare, isolated exceptions sitting inside an otherwise uniform universe? Or are they early evidence of unevenness stretching across a scale nobody previously accounted for? Answering that question correctly matters for reasons that go well beyond academic curiosity. The same foundational assumption under scrutiny here also underpins how scientists calculate the age of the universe, estimate how much dark matter and dark energy actually exist, and predict how the cosmos will continue evolving over the coming billions of years. A crack in that foundation would not stay contained to a handful of oddly early galaxy clusters. It would spread into essentially every major open question cosmology is currently trying to answer. As it happens, cosmology already has another major open question sitting unresolved on the table, one that has nothing directly to do with giant structures on the surface, yet may turn out to be tangled up with this very same mystery in ways researchers are only beginning to seriously investigate. Long before anyone mapped a giant ring or spotted a suspiciously mature galaxy cluster, cosmologists were already fighting over a completely different number. That number is how fast the universe is currently expanding, a value astronomers call the expansion rate. Two separate methods of measuring it, one based on nearby stars and galaxies, the other based on the ancient afterglow left over from close to the beginning of everything, keep landing on two different answers. A persistent disagreement researchers have nicknamed the Hubble tension. This disagreement has stubbornly refused to resolve itself for years, despite repeated attempts using sharper instruments and larger datasets. Both measurement methods have been checked, rechecked, and refined by independent research teams, and the gap between their answers has not meaningfully closed. That kind of persistence is exactly what makes scientists suspect something deeper is going on, rather than a simple, correctable measurement mistake sitting in one particular dataset. Here is where the two mysteries start to brush up against each other. If the universe genuinely contains regions of unusual density, whether from an oversized early cluster or a giant wall of galaxies stretching across billions of light years, that uneven distribution of matter could subtly distort local measurements of the expansion rate, without distorting measurements taken from the more distant, more uniform afterglow of the early universe in exactly the same way. An uneven cosmic web could, at least in principle, help explain why two different methods keep disagreeing. To be completely clear, this connection remains speculative, actively debated among researchers, and nowhere near confirmed as the actual cause of the expansion rate disagreement. Several other explanations remain equally plausible, including systematic errors in one or both measurement techniques that nobody has fully identified yet. Some researchers argue the uneven structure explanation cannot account for the full size of the gap on its own, while others see it as a meaningful contributing piece of a larger, unsolved puzzle. What makes this worth mentioning here, rather than treating it as an unrelated side note, is the growing sense among some cosmologists that these problems may not be entirely separate after all. An unusually organized, unusually early universe would naturally produce ripple effects across multiple different measurements, not just the size of a handful of giant structures. If that turns out to be true, solving one mystery might mean making real progress on the other at the same time, rather than treating them as two isolated puzzles competing for the same amount of attention. Two of cosmology's biggest open questions, tangled together in ways not yet fully understood, both potentially traced back to the same unresolved issue. Something about how matter organized itself in the early universe does not match what decades of careful theory predicted. Zoom out from the raw numbers and equations for a moment, and a different kind of question starts to take shape. One that has less to do with distant galaxies and everything to do with where exactly that leaves us, standing on one small, quiet planet, trying to make sense of all of it. Step back from every wall, arc, ring, and oversized galaxy cluster covered so far, and a much simpler, much heavier question remains. What does any of this actually mean for us, standing on one modest planet, orbiting one unremarkable star, tucked into an ordinary spiral galaxy among roughly 2 trillion other galaxies scattered across the observable universe? The honest answer is that it changes how confidently we can claim to understand the very stage our entire existence is playing out on. For most of human history, people assumed the night sky was fixed, permanent, and essentially unchanging, a calm backdrop to everyday life on the ground. Modern cosmology already replaced that picture with something far stranger, an expanding, evolving universe with a definite beginning roughly 13.8 billion years ago. That earlier shift was already a lot for anyone to absorb. This new discovery adds another uncomfortable layer directly on top of it. Even the confirmed strange picture we settled on decades ago may not be strange enough yet. If some of the giant structures covered in this story turn out to be evidence of a universe that grew up faster or less evenly than assumed, that changes something deeply personal buried underneath all the technical language. It means our galaxy, our small planet, and every single one of us exists inside a cosmic web with a far more complicated, far more surprising origin story than textbooks currently describe. We are not just residents of an old, calm, predictable universe. We may be residents of one that got its start in a far more dramatic, far less understood way. There is also something genuinely humbling buried in the scale comparisons scattered throughout this story. A wall of galaxies 10 billion light-years across. An arc reaching across roughly a third of the whole visible cosmos. A cluster of galaxies already gathering together when the universe was barely a toddler. Standing next to numbers like these, an entire human lifetime, an entire recorded history, an entire species, shrinks down to something almost too small to register on the same scale, and yet we are the ones capable of measuring it, questioning it, and slowly working out what it means. That capability is worth pausing on for a moment, because it is not something to take for granted. A species confined to one small, rocky world managed to build instruments precise enough to detect light older than every civilization that has ever existed, sensitive enough to catch structures stretching across a meaningful fraction of all existence, and rigorous enough to notice when that evidence stopped matching the accepted rulebook. Whatever the ultimate answer to this mystery turns out to be, the fact that we can even ask the question this clearly says something remarkable about where we stand. None of this is settled yet, and it likely will not be settled soon. But the search for an answer is already well underway, using tools far more advanced than anything that came before them, aimed at exactly the kind of question this entire investigation has been building toward from the very first chapter. Every mystery in this story is still actively being investigated, and the coming years are set to bring more data than cosmologists have ever had access to at once. New instruments, purpose-built for exactly this kind of question, are already coming online or preparing to launch, promising to map far larger portions of the sky at far greater precision than any previous survey has managed. The era of wondering whether these giant structures are real is quietly giving way to an era of finding out exactly how common they truly are. Among the most anticipated tools is a ground-based observatory in Chile designed to photograph the entire visible sky repeatedly over several years, building an unprecedented catalogue of galaxies, giant structures, and anything else large enough to leave a trace in the data. Alongside it, a dedicated space telescope built specifically to map the large-scale structure of the universe across billions of light-years is already gathering data of its own, hunting for exactly the kind of giant walls, arcs, and rings that sparked this entire investigation in the first place. These upcoming surveys carry the power to genuinely settle several of the open questions raised throughout this story. If giant structures like the arc and the ring keep turning up again and again across a much larger volume of the observable universe, the rare, unlucky coincidence explanation becomes essentially impossible to defend. If instead, these structures turn out to be isolated exceptions in an otherwise smooth, well-behaved cosmos, that outcome would offer real relief to a model that has served science faithfully for decades. Either answer would be historic, confirming that the universe truly grew up faster or less evenly than the standard model allows, would rank among the most significant discoveries in the entire history of cosmology, forcing a genuine rewrite of how matter assembled itself across cosmic time. Confirming instead that these are rare, explainable exceptions would still represent a landmark test of the model, the kind of rigorous stress test that ultimately makes a scientific theory stronger rather than weaker. Right now, today, nobody knows for certain which outcome is coming, and honest scientists on every side of this debate will readily admit that much. That uncertainty is not a weakness in this story. It is the entire reason it matters. A giant wall 10 billion light-years across, an arc and a ring sitting almost on top of each other, defying easy odds. A cluster of galaxies caught assembling itself at the very edge of observable time. 6 massive galaxies that forced an entire field to double-check its assumptions. Every single piece of evidence gathered across this investigation points toward the same unsettling possibility. The universe may have a far stranger, far faster origin story than anyone currently understands. Somewhere out past the edge of what any telescope has captured so far, the true answer is already sitting there, patiently waiting to be found. Keep watching the sky. It is about to tell us something we are not ready for.